see. Okay, pick up where I left off. Okay, information flow in deep neural networks. This section is dedicated to the information flow estimation in deep neural networks via the proposed method. We estimate the information flow in a convolutional classifier of the MNIST handwritten digits dataset. This neural network is simple enough to be quickly trained and tested, but at the same time is complex enough to suffer from the curse of dimensionality. The dataset consists of images of size 20 by 28 equals 784 pixels. It was shown in Hein and Audebert. These images have a relatively low latent space dimension, approximately 12 to 13. Okay. It was shown to what degree of rigor? Yeah. Let's see. At Clemens, it was proven. Preservation of the only main features is still standard. Only the main features. Sorry. Latent space can even be narrowed down to 3 to 10. Oh, okay. Although the proposed experimental setup is nowadays considered to be a toy and small, it is still problematic for the information bottle analysis, as it was shown in Goldfeld et al. I keep seeing reference to that study, but I cannot find it online. Goldfeld. Oh, actually, I need to open the original paper to find the references, because I didn't print that part. Document, no. Print continue. Let's see. Yes. Okay, where's the references? This appendix. Where's there? Ooh, I should print the appendix. Oh wait, it's only page 10. Oh, yeah, I got the references. Okay. Let's see. Oh, wait, what was the what was it? Gelfeld? Goldfeld. Gosh. Goldfeld. Oh, there it is. Ziv Goldfeld. Okay. Oh, which one? Oh, there's two of them. Let's see. Estimating information flow in deep neural networks, 2019. And the other one, there's no year on the other one. It's probably the second one. Because I don't remember. Convergence of smooth empirical measures with applications to entropy estimation. Yeah. Estimating. Oh, it was in a publication, ICML, 2019. Just this one. Whoop. I hope Taskmaster is not copyrighted. The theme song. Let's see. Estimating from. Okay. Site ad. I feel like I've already seen this one. Did I already download this one? See, 1810. No, I don't have this one downloaded. Definitely haven't printed it yet. 20 pages. Okay, not bad. Estimating information flow in deep neural X. Okay. See. Oh, I wish I could listen to that right now. That's definitely copywritten. Ooh, excuse me. Let's see. Okay. Yeah, definitely put that one next. Okay. As was shown in Goldfield. Okay. So it's still problematic for the IB analysis as shown in Goldfield. 3 to 10. Length space can even be narrowed down to 3 to 10. That's such a broad range. Does that mean as little as 3 neurons are responsible for digits and up to 10 neurons are responsible? Or does that mean that some models actually perform with as few as 3, or with the latent space of only 3? But then why would the upper bound be 10? I'll just have to look at that work. Okay. It can be concluded from the previous section that the weighted Kozanchenko-Leonenko estimator is superior to the other methods tested in this paper. That is why it is used in experience with the deep neural network classifier described in the current section. The analyzed network is designed to return the output of every layer. To avoid the problem of a deterministic relationship between input and output, we apply Gaussian dropout, small variance after each layer. This allows for the better generalization during the training. And find out values of MI mutual information during the information bottleneck analysis. Lossy compression of input images X is performed via convolutional autoencoder with a latent dimension of d sub x latent. Lossy compression of layer outputs L sub I is performed via principal component analysis with d sub L sub I as a number of principal components, as it showed to be faster and not significantly worse than general AE autoencoder approach in this particular case. The general algorithm is described in algorithm 2. So information flow of the neural network during training. Step 1, compress the input data set. Okay, the set of XK data set via the input encoder. Encoding X and C and CX for epoch and in 1, 2 number of epochs due for Li in layers due. Collect outputs of the layer L sub I. Each layer must be noisy, stochastic. Compress the outputs via the layer encoder. Estimate information of expectation value of x with respect to expectation value with respect to L sub I of the layer. Oh my goodness. The verbiage and the information expectation value of the layer with respect to the target with respect to the output with respect to the input, or the output function of the input, where y the output target maps inputs to true targets. Yeah. And for done on the layers, that's 1 epoch. Perform 1 epoch training step network. Okay. Interesting. Okay. We use the architecture of the classification network provided in Table 1. We train our network with a learning rate of 10 to the negative 5. Using the NVIDIA Titan RTX, we use d sub x latent equals d sub y latent equals 4. Okay, layer 1 convolutional 2D 1 8. Leaky Relu. 2 convolutional 2D 8 by 16 convolutional 2D 6 by 32. Is that kernel size? Yeah. Layer 4 dense 32 by 32 Leaky Relu. Layer 5 dense 32 by 10 looks off max. Okay. Pretty small network. Source code. Nice little source code. The acquired information plane plots are provided in Figure 5 as the direction of the plots with respect to the epoch can be detected implicitly. The lower left corner of the plot corresponds to the first epoch. We color the lines according to the dynamics of the loss function per epoch. We do this to emphasize one of the key observations. The first transition from fitting to the compression phase coincides with an acceleration of the loss function decrease. It is also evident that there is no clear large-scale compression phase. Interesting. There's no clear large-scale compression phase. I guess the values were just, they must have been diverging. Yeah. So it's considered fitting. It's considered the fitting phase if both are increasing, but compression if they're, or if one's going up and the ladder's going down. But I guess it wasn't reliable enough. I guess it didn't decrease reliably enough, so there's no clear large-scale compression phase. Moreover, it seems that the number of fitting and compression phases can vary from layer to layer. Seems that the number of fitting and compression can vary from layer to layer. That depends on the interpretation of where was that? Not the manifold hypothesis. Oh, no, that's noisy. So-called fitting compression. Where was it? It said it was shown that. Oh, they claimed that it had been shown that networks go through compression or fitting and compression phases. But how is that determined? Formally, how is fitting and compression defined? I mean, they define it here in terms of information theory, but lies on information. So this concept is logical and applied to the major check two major information about and the letter article for the so-called. Okay. As a result of the information bottleneck analysis, the authors of the latter article put forth the so-called fitting compression hypothesis, which states the training process consists of two phases: a feature fitting phase and representation phase. Okay, so it's just a hypothesis we're taking. We're not assuming it's true. Oh, I forgot to. Yes. Later developed Tishby and applied to deep neural networks in Schwartz's Civ and Tishby. And said the latter paper, right? I said the latter part. Yeah, okay. Schwartz, Tishby. Okay, let's check out Schwartz, Civ, Tishby. I'm going to assume that's an easy name to find. Schwartz is Tischby. Let's see, 2017. Ooh, opening the black box. Let's see if this is Schwartz. Schwartz Civ. Right. Whoosh. Schwartz. Let's see where AORS Schwartz. Oh, Rev. Okay, Ravage Schwartz Civ. And Naftali Tishvi. Opening the black box. Yep, that's the correct one. Okay. That's like that for prior work. Okay, well, we got it. Now this now. Let's check that out. 19 pages. Again, not bad. Information theory of deep learning, mutual information plane, information bottleneck, optimal representations, crucial role of noise, visualizing deep neural networks in the information plane. And noise is something that's easy to biologically justify because our existence is inherently noisy. I mean, being mediated by chemical interactions. Let's see, numerical experiments and results. Okay, looks like a good paper. Let's see. Hebrew University of Jerusalem. Wow. So this comes from an Israeli university. What a coincidence, considering the times. Oh, good. They discussed the Markov chain applicator view of. Yeah. Yeah, so each layer is a node in a Markov chain. Okay. Okay. So then let's see. Yeah. Again, but across a continuous space instead of discrete nodes. Okay. Tishby. What was it? The black box. I'm getting a black box. Deep neural networks. Ah. Okay. Oh man, this freaking paper. I don't even know. Information Theoretic Foundations for Machine Learning. 21st May 2025. Well, I mean, that's the most recent version. Let's see when's the earliest. Oh, I must have opened this from a. Oh, yeah. Let me go to the. I just have to open Arxiv. Manually. There we go. Okay. Oh, yeah. First published July 20 last year. Okay. But it's been updated most recently. unknown distribution, yeah, to data which is sequential to data which exhibits hierarchical structure amenable to meta-learning. Finally, to data which is not fully explainable under the learner's beliefs. Oh. Oh. Particularly relevant. Okay. 96 pages, though. Lots of good info. See 24/7, yeah. Oh my goodness. Oh. I'm gonna print that off. And it is from Stanford, so not from business school, it's from the computer science department. So, oh, and electrical engineering. Cool partnership. Hmm. Hmm. And generally an identically distributed data. Hmm. Okay. Hmm. It's a weird typo. We do this to emphasize on the cameras. Hmm. Interesting. Okay, I missed that part in the first read. We do this to emphasize one of the key observations. The first transition from fitting to compression phase coincides with an acceleration of the loss function decrease. It's also evident that there is no clear large-scale compression phase. But again, that's based on the hypothetical definition of those two. So I might need to refine. Oh, okay, yeah, time change. Theme change, whatever. Okay. Discussion. An information theoretic approach to explainable artificial intelligence, the deep neural network analysis seems promising, as it is interpretable, robust, and relies on the well-developed information theory. However, the direct application of information theoretic analysis still poses some problems. Oh, I'm gonna put my headphones in so I can listen to something without being picked up. Mm-hmm. Mm. Oh, wait. Conference paper at ICLR. I think that was the same one as, what was it? Goldell? What was that? And I can't remember names for shit. Goldfeld. Yeah, ICML, an ICML 2019. Okay. Ooh, but what about 2017? Okay, but then, oh yeah, this most recent one, I just downloaded. Oh, okay, those are printed. Is it 1810? Yeah, infinite. Oh no, that was another one. Ooh, that's some pretty data. Hmm. Oh man, that definitely looks like there's some stuff going on. Ooh, excuse me. Okay. Yeah. So pose some fun. We have shown that it is possible to apply information analysis to compress representations of datasets or models output. Oh, actually, oops. Or continue. Let me make sure my audio doesn't get screwed up when I switched. Still talking on the mic auxiliary. Oh, wait. Mic auxiliary is. But the Logitech says no audio is coming from Logitech. Interesting. Okay, but it's not. Okay, yeah, it is the Logitech. Huh. It's interesting. Let's see, but I want to. That's right. You know, I'm gonna listen to Biba No Money's recent track because I want to. And wait, and I'm hoping you can't hear that. Okay. Whoop. Whoop. That's loud. Hmm. 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 Ah! Okay. Oh, 24/7, that was it. I did download this one. Yes. 96 pages. Connecting learning and information theory. Error is information. Characterizing error, the error rate distortion theory. Comparisons of minimax theory, error. Learning from IID data. Independent and identically distributed data. Learning from sequences. Meta learning. Misspecification, general regressions. Neural scaling laws. Data generating process. Theoretical building blocks. Neural scaling laws. Data generating process. Results such as Theorem 63. Jeez. Insight into trade-offs arising in the development of machine learning models. One example arises in the study of neural scaling laws and, in particular, how to optimally balance the error due to misspecification and estimation for a fixed flop budget. Hoffman, Kaplan. Consider a simple model of computation deep learning where the flop count is the product of the parameter count of the trained model and the size of the training data set. Evidently, increasing the parameter count would reduce misspecification error, potentially at the cost of greater estimation error. Meanwhile, increasing the data set size will reduce the estimation error. As a result, for a fixed flop count, it is not immediately clear how much should be allocated to parameter count versus data set size to minimize loss. John and Roy, 2024, leveraged the tools of this section to study how compute-bound algorithms ought to trade off between these two sources of error. We provide an overview of the problem setting and results here. For a flop constraint, C equals P dot T, where P denotes the parameter count. Okay. I'm going to finish this paper first. Lower left parts of plots. 12. Okay. Oh man, that's interesting. Delta loss per epoch. Delta loss per epoch. Interesting. Okay, okay. I see. Hmm. Hmm. Lower left. It's interesting. Lower left parts of plots B through D correspond to the first few epochs. We use 95% asymptotic CIs for the MI estimates required from the compressed data. Color map represents the difference of losses between two consecutive epochs. Okay, so presumably in the first one it starts in the lower right. Or the upper left? No. Oh, duh. Okay, epochs on the left. Ugh, duh. Okay, so yeah, it starts on the top left. Oh. X information X with respect to layer. Information to Y. Information layer with respect. Information estimate. Now I have not information estimate. Okay, so let's see. What was it? when information with respect, or information layer with respect to X. No, Y is the first one. But information of Y with respect to L is increasing. When they're both increasing, then it's fitting. And when information with respect to the input is decreasing, or the information attributed to the input with respect to the layer is decreasing. Hmm. Hmm. Oh, there's okay. I totally missed the. Okay, L3, L4, L5. There we go. Okay, it's the over plus the overall loss. Which, it's interesting. Oh no, that makes sense. Hmm. Interesting. Yeah. So it goes into these phases where it starts to slow down. The delta loss per epoch. Oh no, I'm sorry, I've got it backwards. The zero delta loss is yellow, and the maximal delta loss is black. Yeah, that is interesting. Yeah, when it gets into those periods of the greatest loss, it's suddenly shifts left, or the information attributed to the input with respect to. I see, yeah, yeah. Yeah, that's really interesting. It still has some consolidation phases, it's just not. Gosh, that's interesting. Okay, so would that basically be, could that be interpreted as sort of learning saturation? Well, no, because that only corresponds to this black portion here. Oh, actually, dang, I wish they would have labeled the epochs per layer somehow. Yeah, because I can't tell if these, they did mention that the compression phases can occur in different layers at different times. So, yeah, this is just measuring the loss with respect to that particular layer. Uh, ay, ay, ay. Okay. We've shown that it's possible to apply information analysis to compress representations, datasets, or models' outputs. To justify our approach, we have acquired several theoretical results regarding mutual information estimation under lossless and lossy compression. These results suggest that this approach is applicable to real datasets, although it has been shown that an arbitrary amount of information can be lost due to compression. The information required for optimal decompression is still preserved. We have also developed a framework to test conventional mutual information estimators, complemented with the proposed lossy compression step. This framework allows the generation of pairs of high-dimensional datasets with small internal latent dimensions and a predefined quantity of mutual information. The conducted numerical experiments have shown that the proposed method performs well, especially when the entropy estimation is done via the weighted Kozanchenko-Leonenko estimator. Other methods tend to underestimate or overestimate mutual information. Interesting. I keep mentioning Kozanchenko-Leonenko estimator. All the other estimators they keep mentioning problems with, I'll keep promoting this one. Other methods tend to underestimate or overestimate mutual information. Finally, information planning experiment with the MNIST dataset classifier has been carried out. This experiment has shown that the dynamics of information theoretic quantities during the training of deep neural networks are indeed non-trivial. However, it's not clear whether the original fitting compression hypothesis holds, as there is no clear large-scale compression phase after the fitting. We suggest that there may be several compression fitting phases during the training of real-scale neural networks. An interesting observation has also been made. The first compression phase coincides with the rapid decrease of the loss function. Yeah, I remember reading that. First compression phase coincides with the rapid decrease of the loss function. It may be concluded that the phases revealed by information plane plots are connected to different regimes of learning, accelerated, stationary, or decelerated drop of the loss function. However, we note that this observation is not the main contribution of our work, and further investigation has to be carried out in order to support this seeming connection with more evidence and theoretical basis. Future work. As further research, we consider using normalizing flows. To improve our approach, normalizing flows are invertible smooth mappings that provide means of losses and information-preserving compression. They can be used to transform the joint distribution to a Gaussian, thus facilitating mutual information estimation. Besides, we will apply our method to various large neural networks and perform corresponding information plane analysis. Oh. Okay, that was the conclusion. And references right there. Okay. Now we got the appendices in the back somewhere. Yeah, complete proofs. Yeah, not like I'm understanding all this, but just glossing over it. Entropy bounds. In this section, we provide several theoretical results that complement the bounds proposed in section 3.2. The following inequalities can be used to bound the entropy terms in statement 3. Statement 7, Cover and Thomas theorem, 8.6.5, let X be a random vector with covariance dimension. Okay, I'll look. Limitations of previous work. In this section, we stress the novelty of our contribution to the problem of high-dimensional mutual information estimation. Okay, yeah. So it's really the application, because the experimentation I want to do is on smaller networks, not high-dimensional, but it's good to keep in mind for when I shift to the mini transformers. Greenwald. Interest SV loss expression the main theoretical results of the first equation following up bound random vector entropy. Z proportional A equal D, compose E be an autocutter input dimension and dimension and was NAS coming from? Hmm. Hmm. Comparison of nonlinear autoencoder and linear primary component analysis? Because that's what PCA means to me. PCA performance and task of mutual information is. I don't remember seeing PCA spelled out in this paper. Oh. Okay. Limitations of other estimators. Modern entropy and mutual information estimators achieve a relative practical success in dealing with recursive dimensionality. We provide reasoning why we chose MINE as the only modern mutual information estimator among them mentioned in the introduction to compare our results with. I mean, they keep mentioning the Lyachenko, whatever. What is that? Chenko? Oh, sorry. Oh, there it is. Kozachenko-Leonenko estimator. The conducted numerical experiments have shown that the proposed method performs well, especially when the entropy estimation is done via the weighted Kozachenko-Leonenko estimate. MINE is widely considered as a good benchmark estimator and featured in several recent works. As MINE is a neural estimator, it is theoretically able to grasp latent structure of data, thus perform compression implicitly. Other lower upper bounds in surrogate objectives. Hmm. According to another over. Jeez. However, note that all these methods are of great use for building information theoretic training objectives as they are differentiable and usually represent upper or lower bounds. In addition to the limitations mentioned above, we would like to note that the relative practical success of modern neural network-based mutual information estimators might be attributed to the data compression being performed implicitly. No, wait, neural net-based mutual information estimators? That does not mean mutual information estimation estimated by a neural network, right? I mean, I know people are doing that in physics and all kinds of other fields that replace analytical approaches, but in the work of Poole et al., it is shown that other complex parametric neural network-based estimators, JW, JS, InfoNC, etc., exhibit poor performance during the estimation of mutual information between a pair of 20-dimensional incompressible, i.e., not lying alone on manifold synthetic vectors. Huh. Poor performance during the estimation of mutual between a pair of 20-dimensional incompressible. These vectors, however, are of much simpler structure than the synthetic datasets used in our work. Hmm. Oh. Oh man. Oh man, that feels weird. Sorry for the distraction. I just realized part of my head feels kind of numbish. I can't tell if that's in my head or if it actually feels different. Mm. Oh, okay, let's see. Oh, and that's everything I've printed so far. There are more appendices. But, classical entropy estimators. In this section, we provide definitions of conventional entropy estimators used to conduct the experiments, as well as provide proofs that these estimators fail in case of high-dimensional data. Okay, yeah, that's what I remember being concerned about before. The estimation of the probability density function for codes C sub k in the latent space plays an important role in the proposed method of mutual information estimation. There are many methods for probability density function estimation. One of the most popular methods for solving these problems is kernel density estimation, KDE, in the section, and I see that mentioned all over the place. The section we study this method in application to entropy estimation. Let rho xk of x be a density estimate at point x, which is obtained from the sampling of the set of inputs without the kth element by KDE with the kernel k. Okay. Make the following expression for the density. Okay, so the density minus k. Okay, now where's B come from? I'm just B mentioned around. Okay, that's probably just assumed from part. Entropy estimate via leave one out method densities at each sample xk are calculated according to the formula. Maximum likelihood. The optimal bandwidth can be selected in accordance with minimization of the Kullback-Leibler difference between the estimated distribution and the empirical one. This is equivalent to selecting the bandwidth as a maximum likelihood estimate. Experiments have shown that this method tends to underestimate mutual information, and the difference increases with an increasing true value of mutual information. Yeah. So it would fail to scale to larger models. Tends to underestimate mutual information, and the difference increases with an increasing true value. Asymptotic. The entropy estimation and bandwidth selection take O of n log n. Compression takes O of n, resulting in a total time complexity of O n log n. Okay. Well, that's that paper done. Let's see. Well, yeah, I need to. That was algorithm 1. And I should probably reread section 3. Reread section 3. Yeah, Peter had to though. Maybe not for someone with prior exposure. Hmm. 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 That's really interesting. really wish there were a way to tell when these drops are occurring. Really wish they would have plotted. I don't know, maybe every 10 epochs they've got. No, not every 10, that'd be too much. Every 50, I guess. Because the first major drop in the output loss, and the overall loss of the entire network on the output, starts at 20 and goes through 50. But these, I have no way to, I mean, they're plotted point by point in terms of the information versus information. So, you know. Uh, hmm. Yeah, I guess I'll just have to implement myself, plot my own data, ideally with checkpoints. Although I guess, oh, they do have source code. They do have source code. So I guess I could clone it, run it, and modify their graph slightly to include checkpoints. Or I could just implement it myself. That's what I'm going to do anyway. Oy. Okay, let's see. Which paper do we want to read next? Language understanding by generative pre-training. I mean, that's an old paper at this point, but I mean, it's important to fully understand the pre-training process. But I haven't started building my transformer yet, so I guess I don't need to know it right now. Yeah, there's the residual feed board with residual layer norm. Hmm. Hmm. Okay. Relation studies. Those are always fun. Hmm. Hmm. Yeah, they set the goal too high. Improving state of the art on that tool datasets. I mean, that's great, but do you understand why? Oh, yeah, that's a paper to read another time. Okay, and net2net. I definitely want to read that, but also a little premature. I mean, I've already read most of it anyway. Oh, no, okay, I read the. Oh, that's right. This is one of the ones. I still need to print more. Right? Oh, no, there's the references. I guess I did print all this. AI. See which 1511? Oh yeah, it's on the continuation pile. Okay, yeah, it really was just 12 pages. Okay. Now we want to put this on top of the training pile. Because, I mean, lore is also a cool method. Oh, and that's another one I need to continue. How much more was there to be? How much more did I need to print that one? Let's see, Laura. Um, 20. Oh, and it went to 30, I think? 26. Okay, just 3 more pages. Okay, so I ended on page 20. Yep. Okay, so 21 to 26. Okay, 21 to 26. Okay, and that one is fully printed now. 2 more to go. Let's see, formal algorithms for transformers and informational bottleneck. Okay, yeah. Yeah, I guess I should finish printing that one tomorrow. 20. This is the one that goes to 30 pages. 23. Okay, again, not bad. 1.5 more, but I'm already pushing it. I'll do those 3 more pages tomorrow. And oh, gotta go get my papers. BRB. Do I need to do a transition? Can I go downstairs? Oh. Oh. Wait. Do I have anything sensitive on my desktop? I should check that first. Whoops. Okay, BRB. Okay, come here. Ugh. Okay. Oh, gotta run this back down. Okie doke. Mm. Oh yeah, happy Independence Day. Happy no more needing to smuggle molasses so we can maximize profits day. Okay. Yeah, so Laura. Okay, we want to put that lower. Okay. Okay, yeah, I definitely want to do knowledge transfer first. We're gonna start with dense networks. And then once we want to start working on transformers, then we'll learn about pre-training, how that process goes, or at least how OpenAI implements it. And then, or implemented. Don't know if they still do the same thing now. Probably. Probably. And then LoRa, which only matters to a trained base model. Okay. Accelerating learning via knowledge transfer. Yeah. Good to scale up, but we don't need that right now. And then yes, the densely connected convolutional neural networks. Great. Um, that's right, concatenation of vectors. Something I wanted to try. And then atom optimization. Oh yes, and that was loss. Okay, atom visualizing loss landscape. Okay, so yeah, I definitely want to keep these two in mind, ready to go. Visualizing loss landscape and atom. Let's see, densely connected. It's relevant to the work I want to do, but hmm. Attention is all you need. Definitely an important paper. Yeah. But densely connected convolutional neural networks, that is directly relevant to the work I want to do. Hmm. 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 Okay. But I still work with simple linear layers before I get to convolutions. So, and yeah, I don't know if residuals. Well, no, these are different from residuals because residuals just naively sum the input, and this concatenates the output of each layer, making it available to later layers, which is what I wanted to try instead of freaking residuals, which are, in my mind, analogous to nonsense. I mean, hey, it's great that they work empirically. It's great that they have results empirically, but it's stupid that we don't understand why. Mm, I wish my neck would heal already. Oh, did my camera freeze or? Yeah, look kind of, yeah. Looks like my stream froze. Hmm, yeah, stream froze. Hmm.